Okay, let me ask you something. Do you really see everything right in front of you? It sounds like a simple question, right? But the answer is a resounding no. Right now, literally, as you look at the screen, there are physical gaps in your visual field. We've all got this built-in physiological blind spot. It's an actual anatomical gap in our vision right where the optic nerve connects to the retina, which means there are absolutely zero photoreceptors there. Now, normally, your brain hides this gap so incredibly well you never even notice it. But today, we aren't just talking about a quirky everyday optical illusion. We're actually using this biological blind spot as a high-stakes interrogation room to question the very nature of human consciousness. Welcome to The Explainer. Today, we're diving into a really fascinating scientific protocol that sets up a literal showdown between three heavy-hitting theories of visual consciousness. Researchers from the TWCF Interpid Consortium have put together an adversarial collaboration. This basically means these rival theories are being put to the test under the exact same lab conditions to see which one actually predicts reality.
All right, let's meet the contenders. Three theories of consciousness.
Okay, let's dive into this. We've got three totally different scientific detectives on the case here, and each one has a vastly different idea of how the brain handles that missing information. Our first contender is integrated information theory, or IIT. IIT predicts that the quality of consciousness is deeply tied to the physical connectivity of the brain's grid-like networks. Since the cortical region that corresponds to the blind spot lacks direct feed-forward connectivity from the eye, IIT suggests there's a fundamental change in perception happening. It predicts that a lack of visual cortex for the blind spot means it literally feels like there is less visual space in that specific region. Think about that. If IIT is right, the physical space around your blind spot is literally warping or shrinking. Next up, we have active inference, or AI for short. Now, this is a predictive processing theory that essentially views the brain as a massive prediction machine that's always optimizing to reduce errors. According to AI, your brain seamlessly compensates for that missing hardware of the blind spot by using its internal models. Because of this, they argue you shouldn't experience any spatial warping or distortions at all. However, because the brain is working with less direct data and noisier sampling around that gap, the perception just gets a little bit less precise. And our third detective is neurorepresentationalism. Let's just call it NREP. Also a predictive processing account, NREP posits that spatial consciousness comes from integrating different spatial frames of reference. It suggests that contextual clues from the intact visual area surrounding the blind spot are actually more than enough to perfectly patch up the gap. So it predicts no major spatial disruption or, at the absolute most, a very modest decrease in spatial bias simply because the brain might be dealing with mildly conflicting sensory clues between the missing spot and the surrounding visual trajectories. And this brilliantly illustrates exactly where these three models totally clash. Just take a look at the scoreboard of predictions. IIT predicts a definitive decrease in perceived spatial extendedness, a real tangible warping of space. AI predicts absolutely no change in space, just a medium loss in precision. And NeuroPap sits slightly in the middle, predicting no change or maybe a modest decrease, banking on surrounding context to fill the void. To figure out who's actually right, scientists need to rigorously test them.
Moving into the interrogation room, let's talk about mapping the blind spot.
Now, to safely and accurately test these wild theories without the brain accidentally filling things in, researchers have to map out each participant's individual blind spot perfectly. The procedure is incredibly meticulous. First, the participant fixates strictly on a central cross. Then, an experimenter slowly moves a small test spot horizontally away from that cross until the participant reports that it has completely vanished into their blind spot. Finally, the test spot is incrementally enlarged in height and width until it just barely becomes visible again, which defines the absolute boundaries of that anatomical gap. What's crucial here is how incredibly strict these researchers have to be to make sure the stimulus stays entirely invisible. They use high-tech, continuous eye tracking. If the participant's gaze drifts even slightly, we're talking by more than 2 degrees of visual angle, the trial instantly aborts, and the cross changes shape to alert them. This guarantees they are purely testing the blind spot's structural gap in the cortex without wandering eyes accidentally stimulating the edges. Now, what's really interesting about this setup is how they use dichoptic stimulation to achieve stimulation around the blind spot without triggering the other eye's vision. Participants wear these calibrated red and green glasses. By perfectly tuning the luminance of the red and green colors on a specially mixed background, researchers can cleanly isolate stimuli to specifically target one eye or the other seamlessly. It's a highly controlled environment designed to practically trick the brain into revealing its underlying mechanics. All right, the rapid-fire experiments. We're testing distance, area, and motion.
So let's shift our focus to the 3 specific spatial tests. First up, experiment 1, the distance task. This one asks a simple but profoundly revealing question. Does the distance between 2 dots appear to physically shrink when that distance crosses over your blind spot?
Imagine how participants experience this sequence. 2 pairs of dots flash sequentially on the screen. One pair, the target, spans directly across the blind spot. The other pair, the foil, is presented entirely outside the blind spot, maybe a little above it. The participant just has to judge which pair of dots felt closer together. If IAT is correct, the dots spanning the blind spot will actually feel closer together than they truly are, simply because that missing visual space is physically compressed in the cortex. Let's move on and see how this builds with experiment 2, the area task. Because, if a simple line of distance might warp, what happens to the perception of an entire shape's area? In this one, the participant is actively using a mouse scroll wheel to adjust the size of a solid central circle. They have to perfectly match its area to a peripheral circle. But crucially, that peripheral circle is made of dashed lines, hovering right around the very edges of the blind spot. It also spins back and forth to prevent the eyes from naturally fading it out, an effect you might know as Troxler's fading. By comparing the chosen central size to the peripheral size, researchers can see if the blind spot acts like a perceptual black hole, basically shrinking the apparent area of anything wrapped around it. And finally, we have experiment 3, the motion curvature task. This shifts our focus from static space to dynamic movement right on the edge of the anatomical gap. Here's how it works. A dot briefly flashes at 4 equidistant positions to create this apparent motion trace. The catch? The trajectory is slightly curved, either towards or away from the central fixation point, skimming right next to the blind spot. The participant simply judges the direction of the curvature. This tests whether a straight or gently curved motion trace gets drastically warped or bent in the mind's eye as it gets too close to the missing hardware. Bringing us to the ultimate brain showdown. Which theory is actually going to win?
So the crucial point here is that this final data is actually still being actively collected in labs over in Glasgow and Toronto right now. The big thing they are testing is the fundamental disagreement at the heart of this research. On one side, we have warped reality championed by IIT, suggesting that missing brain hardware fundamentally and unavoidably shrinks our perception of space. And on the exact opposite side, we have compensated reality, supported by AI and NREP, arguing that our brain's software is just incredibly robust, smoothly patching the hole using context and active predictions. This quote from the research team really highlights the core mystery of this whole adversarial collaboration. They aren't just studying an everyday visual illusion. They're trying to empirically define the mechanics of visual consciousness itself. Is consciousness rigidly tied to our physical neural wiring, or is it a flexible prediction painted over the gaps? When the results are finally published, we're going to have a victor in this heavyweight scientific bout. But until then, I want to leave you with a thought to ponder. As you look away from this explainer and out into your room, is your brain warping reality right now just to hide the gaps?